Welcome to EDC Lab demonstration. I am BVV Satyanarayana, Assistant Professor, Department of ECE, Vishnu Institute of Technology, Bhimavaram. The first experiment in Electronic Devices and Circuits Lab is PN junction diode characteristics. At the end of this demonstration of PN junction diode, you will be able to draw forward characteristics, draw reverse characteristics, calculate static resistance, calculate dynamic resistance, and identify cut-in voltage. The prerequisites are identification of diode terminals, breadboard connections, RPS initial settings, ammeter and voltmeter connection. The aim of this experiment is to study the PN junction diode characteristics under forward and reverse bias, to calculate static and dynamic resistances, to obtain the cut-in voltage of the diode. The equipment required are regulated power supply, 0 to 30 volts range, one number, DC ammeter, 0 to 20 milliamperes, one number for forward bias. DC ammeter, 0 to 20 microamperes, one number for reverse bias. DC voltmeter, 0 to 2 volts, one number for forward bias. DC voltmeter, 0 to 30 volts, one number for reverse bias. The components required are silicon diode 1N4007, one number, germanium diode DR25, one number, resistor 1 kilo ohm, one number, breadboard and connecting wires. The description of the experiment. Diode is a two-terminal device and the two terminals are anode and cathode. Basically, diode is a unidirectional device and it conducts only in one direction. If the positive terminal of the supply is connected to anode, negative terminal of the supply is connected to cathode, then the diode is said to be forward biased. In this condition, the width of the depletion region and height of the potential barrier is lowered by the forward voltage. Hence, the majority charge carriers from both sides of the junction crosses the junction and constitute a forward current which is very large. A small change in forward voltage can create a large change in the diode, and hence the forward resistance of the diode is very small. The minimum voltage required to create a reasonable current in the diode is called cut-in voltage. This cut-in voltage is obtained in the forward bias. If the negative terminal of the supply is connected to anode and positive terminal of the supply is connected to cathode, then the diode is said to be reverse biased. In this condition, the width of the depletion region and height of the potential barrier is increased by reverse voltage. Hence, minority charge carriers from both sides of the junction crosses the junction and constitutes a reverse saturation current which is very small. This reverse current is almost constant with respect to reverse voltage and hence reverse resistance is very large. Circuit diagram for forward bias. In this case, 0 to 30 volts RPS positive terminal, it is connected to anode of the diode. Negative terminal of the supply is connected to cathode of the diode. So this diode is forward biased. We need 0 to 1 volt or 0 to 2 volts voltmeter across the diode so as to measure the voltage across the diode. And an ammeter 0 to 10 milliamperes range is connected in series with the diode so as to measure the current flowing through the diode. And this 1 kilo ohm RS resistance is a current limiting resistance. Here the diode is forward biased, so the voltage across the diode is very less. That's why we are using 0 to 1 volt range meter. and the current flowing through the diode is very large. That's why we are using 0 to 10 milliamperes range meter. And this is the circuit diagram of reverse bias diode. In this circuit diagram, the positive terminal of the RPS is connected to cathode, negative terminal it is connected to anode. 0 to 30 volts range voltmeter is used to measure the voltage across the diode, and 0 to 200 microamperes meter is used to measure the current that is flowing in the diode, which is connected in series with the diode. And RS, it is the current limiting series resistance. In reverse bias, the voltage across the diode is very large. That's why 0 to 30 volts range meter it is used. And the current flowing through the diode is very small. That's why 0 to 200 microamperes range ammeter it is used in the circuit diagram. And coming to the procedure of forward bias diode, connect the circuit diagram on the breadboard as per the figure, and in this connect milliammeter and voltmeter of suitable ranges. By varying the supply voltage gradually in small steps and measure the forward voltage VF in incremental steps and the current IF at each incremental step of 0.1 volt, and tabulate the readings. Draw the graph in between VF and IF by taking VF on x-axis and IF on y-axis. And from the graph calculate the static and dynamic resistances. And coming to the reverse bias, connect the circuit diagram on the breadboard as shown in figure and use microammeter and voltmeter of suitable ranges in the circuit diagram. By varying the supply voltage gradually in steps and measure the reverse voltage VR in incremental steps, and note down the current IR at each incremental step of 1 volt, tabulate the readings. Draw the graph in between VR and IR, taking VR on x-axis and IR on y-axis. From the graph, calculate the reverse resistance of the diode. And these are the tabular forms used for the diode forward bias and reverse bias. Note down the source voltage, forward voltage, and forward current for forward bias diode, and source voltage, reverse current for reverse biased diode. This is the model graph of diode forward and reverse characteristics. Up to certain forward voltage, the current flowing through the diode is 0. That voltage we can call it as a cut-in voltage. After this cut-in voltage, a small change in voltage can create a large change in current, and hence the forward resistance it is very less. Since forward voltage and forward current are positive, the forward characteristics we are getting in the first quadrant. Coming to reverse characteristics, IR is negative, VR is also negative. That's why the reverse characteristics are in the third quadrant. IR it is in the range of microamperes because of the minority charge carrier current. This IR is almost independent of applied voltage VR. That's why the reverse resistance it is in the range of mega ohms. Calculations. For forward and reverse biased diode, we are calculating static and dynamic resistances. And we also calculate cut-in voltage of the diode in the forward bias. Identify one point called operating point on the forward characteristics. The corresponding voltage and current it gives the static resistance. Identify two more points close to each other on the forward characteristics. The change in voltage and the change in current it gives the dynamic resistance. The static and dynamic resistance for the forward biased diode it is in the range of tens of ohms. Up to certain minimum voltage, almost negligible current is flowing through the diode. That voltage it is the cut-in voltage.
Cut-in voltage is 0.5 volts for silicon diode and 0.2 volts for germanium diode. In a similar fashion, we can calculate the static and dynamic resistances for reverse biased diode. Identify one point called operating point on the reverse characteristics. The corresponding voltage and corresponding current it gives the static resistance. Identify two more points close to each other. The change in voltage and the change in current it gives the dynamic resistance. And this dynamic resistance it is in the mega ohms range. Experiment setup. This is the experiment setup for forward biased diode and reverse biased diode characteristics. Let's move on to experiment setup.
This is the experimental setup for PN junction diode characteristics, and this setup it requires a breadboard, 1 ammeter, 1 voltmeter and 1 RPS unit. In this RPS unit, set initial conditions, means this current knob must be in maximum position and voltage knobs must be in the minimum position, and the positive terminal of the power supply is connected to anode of the diode and negative terminal is connected to the cathode of the diode, and hence this diode is said to be operated in forward bias. With this setup we can obtain the forward characteristics. The procedure for this experiment is vary the supply voltage and note down the corresponding voltage and the current. Initially, up to certain minimum voltage, no current is flowing through the diode, and that minimum voltage we can call it as a cut-in voltage. First we are trying to obtain the cut-in voltage. So vary the supply voltage. Up to certain minimum applied voltage, the current in the meter is 0. That minimum voltage we can call it as a cut-in voltage. So almost up to this 0.4 volts, the current flowing through the meter it is equal to 0. So this 0.4 volts we can call it as a cut-in voltage. After this cut-in voltage, as the voltage it is increases, the current rises rapidly, and hence the forward resistance is very low. If you vary the voltage further, a very large current it is flowing through the device. Yeah, almost a very small change in voltage it creates a very large change in current, and the forward resistance it is very less. Now note down the values of this voltmeter and ammeter by varying the supply voltage. So here we are changing the supply voltage in steps of 0.1, and each and every voltage we are noting down the current. If you reverse the terminals of the diode, then this arrangement it becomes the setup for reverse biased characteristics. In reverse biased case, the current is very less. That's why we need to replace this milliammeter with microammeter. And in reverse biased case, the voltage across the diode is very large. That's why we need to replace this 0 to 2 volts meter with 0 to 20 volts meter. Now the diode terminals are reversed, so the diode is said to be reverse biased, means positive terminal of the power supply is connected to cathode and negative terminal it is connected to anode, so the diode it is in reverse bias. Now from this setup we can easily obtain the reverse characteristics. In case of reverse biased diode, the current flowing through the diode it is because of the minority charge carriers. That's why the current is very less. That's why we are using this microammeter. Whereas the voltage across the diode in reverse bias it is high. That's why we are using high voltage voltmeter, that is 0 to 30 volts. So for this one also the procedure is same. Vary the supply voltage and note down the corresponding current and voltage. So vary the supply voltage. as the supply voltage changes, the current that is flowing through the diode also changes, which is very small in microammeters range. So this change in current is almost constant. Since we are using this microammeter, there is a change in current, but strictly speaking, practically speaking, it is almost constant. As the voltage changes, the current is also changes in the microamperes range. So this is the tabular form. As we are changing the applied voltage, the voltage across the diode and the current flowing through the diode changes. This change in current is almost constant, since the current it is because of the reverse biased diode. Now, if you draw the graph for these two cases, then we are getting the characteristics like this. So in first quadrant we are getting forward characteristics, and in third quadrant we are getting the reverse characteristics. I already told the forward resistance it is very less. That's why a very small change in voltage it creates a very large change in the current. The two up to certain minimum voltage, the current that is flowing through the diode is 0. That voltage it is the cut-in voltage. Whereas in reverse biased case, the current it is in the microamperes range. As the reverse voltage changes, the current in microamperes range it is changes like this. Practically this current it is almost constant. From this graph we can easily obtain static resistance and the dynamic resistance. Static resistance means the resistance at a particular point. On this forward characteristics identify one point, and the corresponding current and voltage it gives the static resistance. And select 2 points very close to each other. The change in current and change in voltage for those 2 points it gives the dynamic resistance. Similarly, we can calculate the static and dynamic resistances in the reverse bias also. In case of forward bias, the resistance it is in the range of tens of ohms, whereas in case of reverse bias it is in the range of mega ohms. If you replace this silicon diode with the germanium diode, then with the same procedure we can obtain the germanium diode characteristics also. The difference in between germanium diode and silicon diode it is in the reverse saturation current. If you sketch the characteristics of these two diodes on the same graph, then we can easily differ these two diodes.
These are the practical values obtained from the forward biased diode characteristics: source voltage, forward voltage, forward current. Up to 0.5 volts, the current flowing through the diode it is very small, negligible, and hence the cut-in voltage it is equal to 0.5 volts. After cut-in voltage, a very small change in voltage it can create a large change in the current. That's why static forward resistance it is 120 ohms, dynamic forward resistance it is 15 ohms. These are the practical values obtained from the reverse biased diode characteristics: source voltage, reverse voltage, reverse current. In this, as the source voltage increases, voltage across the diode increases and the current is also increases. But this current it is in the microamperes range. That's why almost there is a negligible change in current with respect to applied voltage. So the reverse resistance it is high, that is in the megavolts. Reverse static resistance it is 1 mega ohm, and reverse dynamic resistance it is also 1 mega ohm. And this is the graph that represents silicon and germanium diode characteristics. If you draw silicon diode and germanium diode forward and reverse characteristics on the same graph, we can clearly differ the difference between the silicon diode and the germanium diode. These are the characteristics for the germanium diode, and for germanium diode the cut-in voltage it is almost 0.2 volts. And these are the characteristics for silicon diode, and for silicon diode the cut-in voltage it is almost 0.5 volts. Silicon diode cut-in voltage, it is greater than the germanium diode cut-in voltage. And coming to reverse characteristics, these are the silicon reverse characteristics and these are the germanium diode reverse characteristics. Germanium diode reverse current, it is high compared to silicon diode reverse reverse saturation current. These are the discussion questions. How do you define barrier potential? What is the difference between static and dynamic resistance? Is reverse saturation current is independent of forward and reverse bias? Why? Explain why the peak inverse voltage of semiconductor diode is an important parameter. And coming to summary, in the demonstration of PN junction diode, we have learned to draw forward and reverse characteristics, calculate static and dynamic resistances, obtain cut-in voltage. Thank you.